This is a reminder about your atomic shapes. We talked about this in chapter 3. I doubt that you've forgotten it. Right here, this S shape, remember that that's like a spherical shape? It looked kind of like that. I should have used the highlighter on it. It's like a spherical shape. And then if we were talking about the P's are kind of like this kind of a shape. Do you remember that? If you don't, go back and check. Or you can just Google S orbitals, P orbitals, you'll get those shapes. Okay. This is what is important about bonding. We've mentioned this before too in a different way. So, a certain unique distance between two atoms allows for the lowest energy bonding. Now at the very top here, I didn't click on this link, but if you click on this link, this is only like 8 minutes long, and she goes into everything you need to know about the whole chapter. Like this whole chapter only gets one video. And if you click on this link, I did already pull this one up. The guy's voice is kind of boring, so I'm just going to scroll to the part that's important. What this plot and this picture is about to show you is something where you start on the right-hand side. So look at the x-axis, you'll see 300, and then going leftwards 200 and 100. That's distance between nuclei. So 300 is actually really far apart. Those are nuclei that aren't bonding and they aren't attracted to each other or anything. And if you look over, like, go leftwards towards the 100, you'll see that this curve goes down. So the lowest point in the curve is the lowest energy. It's where the electrons are attracted to each other's nuclei, but they're not so close that the nuclei are repelling and the electrons are repelling and everyone's upset. Because after you get to that distance, the energy gets really, really high. So it's kind of weird. It's like the plot goes right to left. So watch what happens. So what happens here is we have this farther apart distance. We've got two hydrogen nuclei. They aren't interacting with each other yet, but now as they get closer and closer, you can see they're starting. You can see kind of the outer edge now. Look, the blue, it's starting to interact. Some of the electron density is interacting. And now you can see how it's like really blue between them. Right here, this is that special area. We're almost at the lowest energy point right there. And that's where you can see they're doing a lot of, like, you can tell it's really blue. There's electron density going between both of them. This is what we represent with just a single line. And we just say, hey, that's a covalent bond. And that's all that we say about it. But, remember, it's like 3D space, and they're all, moving into each other's space. It's just two electrons, and note that the dots are the nuclei, not the electron. All right, so now we're going to see what's about to happen. If we try to push them closer together, it's higher energy. They don't want to be that way. So watch. See how those nuclei are, they're about to get on top of each other. So now we have a positive repulsion from two nuclei that are way too close to each other. The electrons don't have enough room, so they're starting to bump into each other. They don't like it. Now look, this is actually what's really going on, is they go back and forth on either side, kind of finding the right position. It's not like it's a perfect distance, and they just take the average to say the length of it. So you can tell right there, that's the average of that distance, that perfect distance where the nuclei are far enough apart, but close enough so the electrons can interact with each other. And you can see on here it says it's 74 picometers is the, and this is just for hydrogen's distance. So that's the first thing, is the distance matters. Like they both have nucleuses that are both positive, and if you get those nucleuses too close, they're going to repel. You want it to be just close enough so that the other atom's electrons can interact with the opposite atom's nucleus, but you don't want them to be too close. It's like a certain distance. That's why it's a certain unique distance, and of course it's unique to whichever atoms you're talking about. Then the other thing is that matters is not just the distance, so you also need the orientation to be right. And what that just means is that they have to be bouncing into each other just so. You want it to allow for the greatest overlap. Greater overlap is possible when orbitals are oriented so that they overlap on an axis. I'll show you in this picture right below, between the two nuclei. So if you look right here. So this is an example of a p orbital and a p orbital overlapping. And you can see how much more of this can be overlapped when they're directly overlapping. That would be on an axis. So that's your axis. They're overlapping on an axis. Whereas these guys don't have as much that they're overlapping on.